good afternoon friends. Welcome to CEC Live Lectures. Dear friends, today in this session we are going to continue with our series on coordination chemistry, quantum mechanics, and today we are going to study about Hermitian operators and postulates of quantum mechanics. And for this very discussion we have once again with us in our studios Dr. Amita Dua. Dr. Amita Dua is Assistant Professor in Department of Chemistry, Dal Singh College, University of Delhi. Dear friends, if you want to ask questions from Dr. Amita Dua on the particular topic, you can call right in the studios. You can contact us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. So let's welcome our guest Dr. Amita Dua, and let's try to understand what Hermitian operators are, as well as I discussed and told you earlier that we are also going to talk on postulates of quantum mechanics. Hello ma'am, welcome to the lecture.
Hello. So, hello to all my viewers. So in the last lecture we have discussed about the operators, and I try to focus more on the linear operators as well as Hermitian operators, because in quantum mechanics, especially in quantum mechanics, we use linear as well as Hermitian operators. So in the last lecture I have done all the numericals on linear operators, and today I will discuss more about the Hermitian operators, and after that I will try to focus on postulates of quantum mechanics. So what are Hermitian operators? So there is a condition for an operator to be Hermitian. Suppose we have two eigenfunctions, that is phi as well as psi, and an operator A operator. Then what is the condition? You have to see the condition, because finally I'll apply the same condition on all the numericals. You have to keep this condition in your mind, that just see the slide, you can see the condition, that integration of minus infinity to plus infinity psi star, that we have two eigenfunctions. I've already said that there are two eigenfunctions, phi as well as psi. So what is the condition for an operator to be Hermitian? That is psi star, and then in brackets A operator and then phi bracket close d tau, because we are doing the integration part, equals to integration of minus infinity to plus infinity, and then first it will come phi. Earlier it was psi star, now it comes phi, A operator, and then psi star. Just see the slide, you can see the condition on the slide, d tau. Then the operator, in case this condition is satisfied, then the operator A operator is said to be Hermitian in nature. To explain this, I'm just taking a simple example of it. Suppose I have two functions, that is psi e to the power of minus ix and phi, that is sin x, and the operator A operator is d square by dx square. So the most important thing is that what is my question? My question is that I have to show that this operator d square by dx square is Hermitian in nature, and to explain this I am taking two wave functions, one is phi and another one is psi. And what is my phi? My psi is e to the power of ix. Just see on the slide, the example is given, it is shown on the slide, e to the power of ix, and phi is sin x. Now what is phi star? Always the star is the complex conjugate. So in case my psi is e to the power of ix, complex conjugate is always taken whenever there is iota, that is symbol I is there in the function, then only the star factor is there. Otherwise on complex conjugate the wave function will remain the same. So in this case my psi is e to the power of ix, so it becomes, what would be psi star then? My psi star would be e to the power of minus ix. Now the most simple thing, the easiest way how to solve, how to check whether an operator, whatever operator is given to you, you have to check whether it is Hermitian or not. Just take the left hand side and then solve the right hand side and just see whether they are coming out to be equal or not. So in this case, because I have two functions phi and psi, So what was my left hand the condition for Hermitian operator? My LHS was, that is psi star A operator into psi into dx. Why I am using dx? Because my function is containing e to the power of ix and the second one is sin x, because only x component is there, that is why instead of d tau I am taking dx. So this becomes psi star, my psi star is e to the power of minus ix, and then I am simply putting the values which I have already told, that what is my psi, what is my phi and what is my A operator. I am putting this in the Hermitian condition. I am taking the left hand side, just put all the values on the left hand side expression. So instead of psi star, put e to the power of minus this thing ix, and then instead of A operator take d square by dx square, and instead of phi take sin x, because it is there in the question. See the slide, and then dx. Now if I double differentiate sin x will get converted first into cos x, and then cos x will get converted into minus sin x. So you can see what would be the expression. It would be minus integration of e to the power of minus ix sin x dx. We don't have to solve the whole integration. We just have to go to a normal expression just to see whether the expression of both the left hand side and right hand side are coming out to be same or not. We don't have to solve any integration part. Now again I am taking the right hand side. My right hand side is, earlier it was phi star A operator psi, and now I have phi A operator psi star. Put all the values, instead of phi write sin x, and then A operator I am writing d square by dx square. Instead of psi I am taking e to the power of minus psi star, because I have psi star, that is why e to the power of minus ix. And nothing is happening to A operator. Why? Because there is nothing like iota in A operator. So A operator, it is already d square by dx square, so it will remain as such. Now when I solve this part, the double differential of e to the power of minus this thing, so because e to the power of minus ix, so minus will come twice, it would already becomes positive, and because iota is also there, so on double differential I square is minus 1, so in front of the expression there is minus sign. So on double differential of e to the power of minus ix, it is minus e to the power of minus ix. Now what would be the answer of right hand side on solving the RHS? What do I get? That is minus sin x e to the power of minus ix. So what we have seen, that on solving the left hand side and right hand side of the Hermitian condition by putting all the values, the expressions on both the sides, that is LHS as well as RHS, it is coming out to be equal, and therefore d square by dx square is a Hermitian operator. Why? Because it is satisfying the Hermitian condition which I have already told. Now the properties of Hermitian operator, there are two theorems, usually it is given in the books as theorems. There are two theorems which Hermitian operator always satisfy. The first is either it is given in the form of theorem or it is given as the properties of Hermitian operator. So this is the first property which you can see on the slide, that first of all the eigenvalue of a Hermitian operator are real. That if an operator is Hermitian in nature and if it is applied on some wave function, then the value which is obtained is always real. So the eigenvalue, this we have to prove, and I am showing you the proof on the slide. Just see the slide, that eigenvalue of a Hermitian operator are real, that is they are positive or negative, that doesn't matter. Real means it doesn't contain any iota. It is a real value, it is not imaginary number. So suppose there is an operator A, and I am saying that it is a Hermitian operator, because if it is Hermitian then only it will give you the eigenvalue, the real value, and this is what I want to show, that it always gives you the real value. So suppose there is an operator A, it is an Hermitian operator, and suppose we have an eigen function, that is psi, and A is, suppose it is a real eigenvalue. Just see the expression. Suppose A operator, I have marked an arrow, suppose it is an Hermitian operator, suppose psi is an eigen function, and if A operator operates on the eigen function, then the value which is obtained is always and always real eigenvalues. It is an eigenvalue, but now it has become the real eigenvalue. This is similar to the eigenvalue equation which I have discussed in the last lecture, that what are eigenvalues. This is similar to this, but the only thing which I want to tell you, that the operator, the nature of the operator I am discussing. The operator which we are going to use are always Hermitian operators. In quantum mechanics we deal with the Hermitian operators, and Hermitian operators always, usually they give the real values. Now we can do the, now I am doing the proof of it. Suppose operator A is an Hermitian operator and psi is an eigenfunction and A is the eigenvalue. Now what would be the eigenvalue equation? That would be A operator. It is operating on the wave function psi. We are expecting to give the value as A and then the wave function back. Then only it is known as eigenvalue equation. This equation I have marked as equation number 9. Now I am taking the complex conjugate of this equation. So it will become operator A. Just take the complex conjugate on both the sides. I am putting a star. I am doing nothing. I am just putting a star on the whole equation, on the left hand side as well as on the right hand side. So this will become operator A psi, and then on total there is a star, and then again on the right hand side it is becoming A star and psi star, and this I have marked equation number 10. Now I will multiply equation number 9 with psi star and then integrate. So what will you get? Just put a integration sign and then multiply psi star with equation number 9. This will give you integration of psi star operator A psi in brackets obviously equals to, and then again psi star A psi bracket close, and then d tau. D tau because I am not restricted to any x, y or z, it is a generalized thing, that is why I am using a volume element, that is d tau. Now I have done nothing. Only on the right hand side I am taking the small a out of it. Why? Because it is a constant value. So this will become psi star in brackets operator A psi d tau, left hand side will remain the same, equal to, take small a out of the integration part because it is a constant value. So this will become small a integration psi star into psi equals to d tau, and I have marked this equation as equation number 11. So what I have done is simply I have one equation which I have marked equation number 9. I have taken the complex conjugate of it and marked as equation number 10. So I have two equations. Then I am taking equation number 9, multiplying it by psi star and integrating it on both the sides. Now nothing to do with equation number 9. From equation number 9 I have derived equation number 11. Now I will shift to equation number 10. The similar thing, what I have done with equation number 9, I have multiplied it with psi star. Now multiply equation number 10 by psi and integrate it. So my equation number 10, on multiplying equation number 10 by psi and on integration, I get psi, again in the brackets, A operator psi star d tau, and then again integration psi in the brackets A star psi star d tau. As the similar thing I am doing, again I am not disturbing the left hand side, I am just taking A star out on the right hand side and marking it as equation number 12. So from equation number 9 I got 11, from equation number 10 I got equation number 12. Now I will equate the two equations which I have got, that is 11th as well as 12th. The left hand side, just see, the left hand side of equation number 11 and 12 are same. There is nothing to it because both the wave functions are psi, so there is nothing different. So because the left hand side of equation number 11 as well as 12 are same, so I am equating the right hand side of 11 and 12. So what we obtain is that simply A equals to psi star into psi d tau, and then A star psi into psi star into d tau, and therefore A equals to A star. So always whenever there is Hermitian operator, the values which are obtained are always and always real, because here also A equals to A star. What is A star? Star is the complex conjugate. So a normal number as well as its complex conjugate, it comes out to be same, that is they are real if the operator which we are going to use is Hermitian in nature. Now the second thing, the second theorem, that the eigenfunctions of the Hermitian operator, you must have seen that when I was telling you about the condition of Hermitian operators, there were two wave functions. I was using two wave functions, that is psi and phi. Instead of psi and phi, here I am using two wave function, that is psi 1 and psi 2. It all depends upon you, whatever kind of wave functions you want to use. These are just the symbols which we are using, but they must be different. So the eigenfunctions of the Hermitian operators corresponding to different eigenvalues are orthogonal to each other. So suppose this is what I want to prove, is just see what he wants to say. Suppose we have two eigenfunctions, that is psi 1 and psi 2, and I have an operator, A operator, which is Hermitian in nature, and the values corresponding to psi 1 is A1 and corresponding to psi 2 is A2. Now I have to show that if operator A is Hermitian in nature, then the two wave functions on which it operates, that is psi 1 and psi 2, they are orthogonal to each other. Now what is the condition of orthogonality? And I have already discussed the three kinds, that is the normalization, the orthogonality and orthonormality in one of my lecture. And what was the condition of orthogonality? You can see on the slide the condition of the orthogonality is given, that is integration of psi 1 into psi 2 star equals to 0 or psi 1 star psi 2 d tau equals to 0. So this is what I want to prove if already A operator is Hermitian in nature. So just see the proof of this condition. Suppose the eigenvalue equations are, because I have already told, because psi 1 and psi 2 I have told that they are eigenfunctions. So if they are eigenfunctions and their eigenvalues are A1 and A2, then obviously they will satisfy that eigenvalue equation. Now what is my eigenvalues equations are? That is A operator psi 1, that is whenever an operator operates on the wave function will come as such with a constant value multiplied, and it will be real if that A operator is Hermitian in nature. Because I am already saying that my operator A is Hermitian in nature, my wave function psi 1 is already an eigen wave function and the values which are coming out to be real, so it will satisfy the eigenvalue equation. So what would be the two eigenvalue equations? My eigenvalue equations would be operator A psi 1, what is the eigenvalue? A1, and the wave function will comes out to be the same because it is an eigenvalue equation. Similarly, A operator psi 2 and then eigenvalue, that is A2 psi 2. Now because we are doing the derivation part, so I have marked these two equations as equation number 13 and 14. Now we have two equations, right? Equation number 13 and 14. First of all I'll take equation number 13. What is my equation number 13? My equation number 13 is A operator psi 1 equals to A1 psi 1. I'll multiply both the sides of equation number 13 by psi star, by psi 2 star in fact, and integrate both the sides. So what it will become equation number 13, just see the slide, just concentrate on the slide, then only you will be able to understand, because it's a bit complicated maths. So take equation number 13, multiply by psi 2 star. First I'll multiply, just see. It was A operator psi 1 d tau. I have multiplied psi star, I have multiplied psi 2 star on both the sides. Because I am doing the integration part, so I am also writing d tau on both the sides, right? Now on the right hand side, I am simply taking A1 out of the integration. So this expression will become integration psi 2 star bracket A operator psi 1 d tau, and then A1 is out of the integration sign, and then psi 2 star psi 1 d tau. So after multiplying and integrating, this will become equation number 15. So from equation number 13, after multiplication and integration, we land up to equation number 15. Now in the equation number 15 only, again take the left, just leave the right hand side part of equation number 15. Take again the left hand side of equation number 15. What you can see? What is the left hand side? It is integration psi 2 star in brackets A operator psi 1 d tau. Now what is this? That just reverse, just interchange the position, because A operator is Hermitian in nature. Just apply the Hermitian condition onto it. Take psi 2 out and psi 1 out and psi 2 inside the bracket. It is the condition for Hermitian operator, because we have already taken that our A operator is Hermitian. Then only we have to prove that psi 1 and psi 2 are orthogonal to each other. So if my A operator is Hermitian, then I can simply take the left hand side equal to what? The left hand side can also be evaluated to be, that is psi 1 and psi 2 will come inside, and it will become, this is the condition for Hermitian. Now once this is updated, we have already taken equation number 14. You can see on the second line of this slide, that is equation number 14. The equation number 14 is A operator psi 2 equals to A2 psi 2. Just use this equation number 14 expression in this right hand side of equation number 15. So the bracket, that is A operator psi 2, will become small a2 into psi 2, and star will remain as such. It is not disturbed. Now simply take a2 star out of it, out of the integration. What it will become? a2 star psi 1 psi 2 star d tau, right? So because whenever Hermitian operators are there, in the theorem number 1 I have already told, whenever the operator which is used is Hermitian in nature, the values are always real eigenvalues. It means a2 star, we can write a2 star as simply as a2. So I have replaced a2 star by a2. Why? Because the values are real. So by this will become equation number 16. So I have done nothing. Again I am repeating that I have taken two equations, equation number 13 as well as equation number 14. I am doing nothing with equation number 14. I will just use in one of the places. Whatever I am changing is equation number 13, that I have taken the 13th part, I am multiplying it with psi 2 star, I am integrating it, first thing, and then equation number 13, and then whatever equation is obtained, that is the 15th equation, I am changing, I am again equating to one more thing, that is using the Hermitian condition, and I am landing up to equation number 16. So I have two equations, equation number 15 and equation number 16. So now we will equate, because obviously I haven't disturbed the left hand side, not even once. So and from equation number 13 only we are getting two equations, that is 15 as well as 16, but the left hand side is not disturbed. So just equate the right hand side of 15 and 16 equal. So this will give you a1 psi 2 star psi 1 d tau. You can see on the slide what was my equation number 15. Just see the right hand side of equation number 15. I am just copying it because I have to equate these two equations, that is a1 psi 2 star psi 1 d tau. See the right hand side of equation number 16, a2 psi 1 psi 2 star d tau. So I have simply equated the right hand side of 15 and 16. Now take the right hand side on the other side, that is a1 minus a2, the brackets, that is psi 1 psi 2 star d tau equals to 0. So what I have obtained is that the whole thing is 0. Obviously they are saying that a1, if a1 is not equal to, there are two expressions, right? One is the bracket, that is a1 minus a2, and the second is the integration part, that is psi 1 into psi2 star d tau equals to 0. Now the whole expression is going to be 0. So it means what? Something, either of them is 0. So if a1 is not equal to a2, this indicates that if that bracket part is not 0, but even then the whole expression is 0, this indicates that psi1 into psi2 star d tau must be 0, and which shows that the two wave functions are orthogonal to each other. They are satisfying the orthogonality condition only and only when a1 is not equal to a2. But in case the bracket becomes 0, that is a1 becomes equal to 0, then they are not orthogonal to each other. Now we'll do some of the problems which are based on Hermitian operators. They are very common problems. Basically, I can tell you, most of the time on Hermitian operators, you should know what is Hermitian operator, what are the properties of Hermitian operators, that is the two theorems which I have discussed with you as well as their proofs. And there are 2-3 very important questions which I am going to discuss now. First is like, because when I am explaining, I am taking the generalized thing, let operator A, I am taking the operator A, but now I am taking the main important operators which we are going to use in quantum mechanics, like momentum operator, the Hamiltonian operator. Now applying the Hermitian this thing on these kind of operators. You can see in the form of numericals, like most of the time this kind of numerical come, show that operator Px operator, that is you have to show this Px operator, that is linear momentum operator, is Hermitian in nature. The most simplest thing to do all these kind of numericals which students think that they are very difficult and complicated, the simplest thing is just concentrate on the condition of an operator to be Hermitian. What was the condition? So suppose we have, because none of the wave functions are given, obviously only operator is given, so you have to take the two simple wave functions, that is psi as well as phi. So whenever wave functions are not given, just take the imaginary wave functions, because my main thing, our main focus is to prove that our wave function, the operator is Hermitian in nature. So we have to take the two wave functions, that is imaginary wave function, that is psi as well as phi. See the slide, you can see the proof, how to do this numerical. Just see, if psi and phi are the two eigen functions of the operator A, then what is the condition of Hermitian? For an operator to be Hermitian, what is the condition? I have already told when the lecture starts, I have told the first thing which I have told is integration minus infinity to plus infinity psi star in brackets A operator phi d tau. On the right hand side, minus infinity to plus infinity phi in brackets A operator psi star d tau. Now there are two ways. Either you can solve right hand side as well as left hand side and just see whether they are coming out to be equal or not, or the other thing obviously which people do in math, simply start with left hand side and just see whether you are landing up to right hand side or not. So this is what I am doing. It all depends upon you. You can do in either ways. Like in this numerical, I am starting with left hand side and I will land up to right hand side. So here, what is my operator A? Just see the things. What is my operator A? It is my momentum operator. We have discussed in the last lecture, I have discussed the topic operators. So what is my operator A is Px operator, that is H operator I, Px star minus H cross I d by dx. And we have to prove the same expression. So I'll discuss this problem and more problems after the break. We'll again start with the Hermitian operators. Thank you. will discuss about the problems on Hermitian operators. Just see problem number 1. I'll continue with that problem, the same problem. That is, we were discussing about whether we have to show that the linear momentum, that is Px operator, it is one of the very important operator which we will use in quantum mechanics later on in all the chapters which we will do, like rigid rotator, vibrational motion, or harmonic oscillator, or hydrogen atom. These are the very common operators which are used, that is the 2-3 operators like momentum operator and Hamiltonian operator. So first we have to prove and we have to show that this momentum operator is Hermitian in nature. So what is the way how you can show that? So whenever you want to deal with all these kind of problems, like you have to show whether they are Hermitian or not, just take two imaginary wave function. So in this case I have taken psi as well as phi. The two eigen functions are there, and what is my operator? That is A operator. And in this case my A operator, just see the slide, you can understand it very easily. Suppose I have an operator A operator, that is a Px operator, and what is the expression of P operator, that is Px operator? I am taking the x component of it. You can take y, you can take z, you can take the total momentum, but here I am taking the expression for Px. Now that is h cross upon I d by dx. This is the expression already discussed in the last lecture when I have told you all the expression for the major operators which use in quantum mechanics. That is h cross by I d by dx. And then the most important thing, you should know what is Px star. What is star? Because in the expression of Hermitian operator, first collect the things which are required. That is, you need psi star, you need A operator, you need A operator star. So just first of all always collect the data and then start with the numerical. This is the simplest thing to deal with these things. So because I have A operator as Px, that is h cross by I d by dx, is there any iota? Yes there is, that is h cross by I. So what would be my Px star? Just take a negative sign. Everyone knows, I am telling you again and again, always whenever there is an iota in the expression, whenever there is an iota, then only star could be taken. So what would be my complex conjugate? It would become minus h cross by I d by dx. So it is required to prove that. What I have to prove? Just put, instead of A operator, write Px. Instead of d tau, write dx. Why? Because I am taking Px. Because it is x, so I will take dx. If a student is writing py, if in an exam they are asking you to prove that py operator is Hermitian in nature, then instead of d tau, just write dy. This is the very simple thing which you have to notice. And if it is p, then write d tau. If it is px, write dx. Now I'll start with, now we'll discuss, first of all discuss the left hand side of the operator. What is my left hand side? I'll solve the left hand side and I'll show you that it is coming out equal to the right hand side, and by this I can prove that my Px operator is Hermitian in nature. So I'm starting with the left hand side. Just see, minus infinity to plus infinity, psi star Px operator in the brackets, this is the condition, Px operator phi d tau, right? Now just see the slide, I am just simply putting the values. This becomes minus infinity to plus infinity, psi star will remain psi star because it is a normal wave function which is I am taking. What is the expression of Px? Px is h cross by I d by dx, and then it is written phi, write as such whatever it is written on left hand side, and just put the value of Px, and then it will become dx. Now because h cross by I is a constant, so I am taking it out of the integration. This becomes h cross upon I minus infinity to plus infinity, then it becomes psi star. We are left with phi star d psi by dx, and then dx is already written. Now how to solve this integration? We are left with this part. Now whenever we deal with Hermitian, one should know a simple maths formula, that is integration by parts. I'm telling you in brackets, highlighting this formula, because most of the people, they just forget all these formulas after 11th and 12th. So just see to this formula. I'm focusing on this formula, so that there is no confusion. There should not be any confusion while solving all these expressions, because this is the only thing which one should know, or one faces the problem during this thing, Hermitian, when we deal with Hermitian part. So what is the formula of integration by parts? This is the formula, integration. Suppose we have two things, two wave functions, that is u into dv. Then what would be the thing after integration? It is u into v minus integration v into du. Just mug up this formula. Everyone should know this formula while solving the Hermitian part. So in this case, because I have to solve the integration part by this formula, so obviously one should know that in the above expression, what is u and what is v. So what is my u? What is my u? Just compare it with the formula. When on comparing, you could see that your u is psi star, and what is your v? Your v is simply phi, that thing, the circle and then a cross, that is phi. So you can see that your u is phi star and my v is phi. Now I'll put the above integration. To solve the above integration, I'll use this formula. Just see the expression. What would be my formula? H cross by I will remain as such. There won't be any integration sign. Why? Because I'm integrating the thing, obviously. Now what would be my answer on integrating? I'm starting with the brackets. First of all, u into v. What is u? Psi star. What is v? That is phi. And then obviously the limits are used, minus infinity to plus infinity. And then a negative sign. I'm just writing the same formula, just concentrate, minus. Again there is an integration, minus infinity to plus infinity. And then you have to write v. What is my v? That is phi. Put phi. And then du. What is du? Obviously we are differentiating. What? We are differentiating the u part. It will become d phi star. And obviously for the integration part you have to write dx. So it will become d phi star divided by dx multiplied by dx, because it is an integration. So obviously dx part will be there. So this is the expression. Now the first term which I have cutted, you can see on the slide, I have cutted and marked it as 0. In this, on integrating this, both the wave functions, that is psi and phi, they vanish at infinity. So their value would be 0, because whenever it is the condition, when I was discussing about the properties of the wave function which are used in quantum mechanics, I've already told, and maybe in the next lecture when we will discuss about the postulates of quantum mechanics, then also you will come to know that the wave functions which we will use in quantum mechanics, that is, they will vanish at infinity. So this is the condition, and because in this numerical also we are taking as to be eigen functions, that is the normalized and the well behaved wave functions. The well behaved are the one which vanishes at infinity. The same thing which I am going to apply. So that is why the first part of this expression will vanish. Why? Because psi and phi star on integration, that is minus infinity to plus infinity, this will give you a 0 answer. Now what we are left with? Just see the slide, that since both the wave functions psi and phi, they are eigen functions, the value becomes 0 at infinity. We are integrating, my limits are minus infinity to plus infinity, this will become 0. So the first term is becoming 0, and now we are left with what? This I want to show you, that we are left with, because there is a negative sign with the second term. So negative sign will come out. It will become minus h cross I, integration of minus infinity to plus infinity, right? Minus infinity to plus infinity psi, and then d psi star by dx. Again, I want to show you the earlier slide. Just see the slide. This is the most important question. Once you know this numerical, you will solve the next very easily. So, I am taking minus sign out, h cross by I, integrating minus infinity to plus infinity, and then phi d psi star by dx. This you can see. Now, I am just rearranging the things. I am again taking, earlier I have taken h cross by I out of the brackets because I have to solve the integration part. Now I have solved my integration part. I am again taking h cross by I inside the brackets because I have to show that it is equal to right hand side. So again I am taking h cross by I with its that negative sign it is carrying inside the integration. So it becomes phi minus h cross by I d by dx. I am taking psi star out because p psi star into dx. Now what is my minus h cross by I d by dx? In the starting only, again see, I have already taken, what is my px? H cross by I d by dx. What is my px star? Minus h cross by I d by dx, and this is what I am showing you in the slide, that this minus h cross by I d by dx, you can write it as px star psi star dx equals to, and this is equal to my right hand side. So thus this shows that the p operator which we will use in the quantum mechanics is Hermitian in nature. That is, whenever I'll apply this Hermitian operator or any wave function, it will give me a real eigenvalue. This so whenever an operator is Hermitian in nature, then it is 100% sure that it will give you the eigenvalue, that is a real eigenvalue it will give. Now you can see there are two numericals. One I have discussed, that is the px, and then second you just see the kinetic energy operator, that is will take, after that I will also take the potential energy operator and the total operator, that is a total energy or Hamiltonian operator also. This is a numerical which is containing three parts. In the first part I will discuss the kinetic energy operator, in the second part I will discuss the potential energy operator, and in the third part we will do the sum of it, that is the total Hamiltonian operator, which will show you that my energy, that is a Hamiltonian operator, is also Hermitian in nature. So just concentrate on this numerical. I am taking the kinetic energy part, which is all the calculations are involved in this. In the potential energy part there is nothing as such. Just see. So if again the same thing, suppose I have two wave functions, that is psi as well as phi, which we have to take to solve this numerical. That is psi and phi are the two eigen functions of the operator A, and then operator A is Hermitian. What is the condition? The same thing, that is integration minus infinity to plus infinity psi star in the brackets A operator phi d tau, right hand side minus infinity to plus infinity phi, and then in the bracket A operator psi star d tau. I'll start with left hand side and I'll try to land up on the right hand side. If the right hand side and left hand side comes up to be the same, then my operator, that is kinetic energy operator, would be Hermitian in nature. The same thing which I have done with the px operator. Let's start with it. Suppose I have operator A operator. Now what is my kinetic energy operator? It is minus h cross square 2m. d square by dx square. One thing more, just to decrease or making it, just to make it more simplify, I haven't taken h cross as, I can take it as h by I can finish that cross part. So I have simply taken as h cross. So this will become, what is my Tx? Tx is minus h cross square by 2m d square by dx square, because I am taking the x component, just to simplify obviously, because if I take the whole thing, so it becomes more complicated. So I am just taking the dx part. So this is Tx operator, that is minus h cross square by 2m d square by dx. Because there is no iota, intentionally I haven't taken the iota part. So this becomes, what is Tx star? The star part, that is complex conjugate, would be, it will remain the same because there is no iota. So whether I have Tx or I have Tx star, that will remain the same. So it is minus h cross square by 2m d square by dx square. Fine. Now what we want to prove is, instead of a operator, just put Tx operator. This is what we want. I'll start with left hand side, just concentrate on the left hand side, that is phi psi star Tx operator phi dx, right? Taking left hand side and integrating it by paths. Because this can only be solved, there are two functions. Whenever there are two functions and they are multiplied, we have to apply this formula. That is, whenever there are two functions, then we have to apply this formula, that is integration by paths. Again and again you can see I have written the formula in the brackets, everyone can see this. Now taking left hand side and integrating by paths. Now just start psi star Tx phi into dx, just put the value. We have psi star, in the brackets write Tx operator. What is my Tx operator? I have already written, that is minus h cross square. It is h cross, this is not h square. See the slide carefully. It is h cross square by 2m d square by dx square. This is the expression you can get in my last lectures or in any book, wherever, whatever. And then bracket close, we have phi and then dx. Because h square by 2m is a constant value, I am taking it out of the integration part and then solve the left out integration by using integration by paths. So minus h cross square by 2m is taken out. We are left with psi star d square by dx square. I am taking phi with it and then dx. Now on integration, this will become psi star because it is d square by dx square. So I am splitting into two. That is, I am writing d by dx and then in brackets d phi by dx, and dx is already written. So integration by paths, what is the formula? U into dv. Answer is uv minus integration v into du. Now I am comparing the above expression and checking what is u and what is v and then solve it. Now what is my what is my u? My u would be psi star. Just compare it, just see the slide. What would be my u? My u is psi star. And what is my v? V is d into u. Now here d is d by dx. And what would be my u? That would be d psi by dx. And then I'll put these u as well as v in the formula. So on integration, applying the formula, minus h cross by 2m will remain as such. Just put the brackets to see the formula. Just see what is u. U is psi star. So I wrote psi star. What is v? D psi by dx. Just see, I have written psi star d psi by dx, as simple as that. And then put the integration size, that is the limits minus infinity to plus infinity. And then in the formula, minus sign. Again take the integration, just see the formula and write, put the values. And then integration minus infinity to plus infinity. Now I have v. What is v? D psi by dx. Then it is du. What is u? That is psi star. So d, that is d psi star by dx into dx, because already integration is there. So obviously you have to write the dx outside at the end of the integration part. So in this expression also, the one which we have obtained by applying the integration by paths, the first term of this expression will become 0. Why? Again, because the two wave functions are eigen functions. So whenever the limits minus infinity to plus infinity are applied on them, the answer will definitely, it will come out to be 0. So by this, the first term of the integration will come out to be 0. Just see the slide, I have put it a bracket under that first expression and it is coming out to be 0. Now we are left with what? Just see the second expression. I already have a negative sign out of the brackets, and inside the bracket also there is a negative sign. So minus minus would become plus, and h square by 2m integration of this you can see on the next slide, but just see what is written on this one, then I'll show the second one. So minus and minus, because the first term is cancelling, it is becoming 0. So minus minus will become plus, and then h cross square by 2m, and then integration d psi by dx, d psi star by dx into dx. Just see. Since both the functions and phi, they vanish at infinity because they are well behaved functions, and thus the first term will become 0, and I am integrating the second term by parts. This is I have told you. So now the second term which we are left with, now I will apply the same formula, that is integration by parts onto that. And what that second term, just focus, first term has become 0. We are left with the second term, and now I can only solve this second term by integration by parts formula. So see the slide, very important thing, that is the second term which is left, that is d phi by dx, d psi star by dx into dx. Compare it. What is u in the expression? What is u? That is phi. What is v? That is d psi star by dx. Again just apply the formula. We have a positive sign, so it will remain h cross square by 2m, and then formula. What is my formula? That is u into v. What is my u? U is phi. What is my v? d psi star by dx, minus infinity to plus infinity. Again, what was my formula? That is minus integration v into du. So what will it become? Minus. What is my v? d psi star by dx. What is my u? That is du. d phi by dx, and then dx for the integration part. Again in the expression, the first term will become 0. The same thing which is applied, because they are eigenfunction, whenever they are integrated in the limits between minus infinity to infinity, this will minus to plus infinity, it will become 0. So we are left with what? We are left with d psi star by dx into d phi by dx into dx, right? Now I am taking that phi out, just on rearranging, because we have to rearrange, otherwise we will never land up to right hand side. And just see, there is a negative sign also with the second term. So I am taking the negative sign out of the brackets. This will become minus h cross square upon 2m integration. Phi I am taking out, I am taking d square psi star by dx square into dx. Again, because I have to show it to be equal to the right hand side, as I have done in the above numerical also, again I am taking minus h square by 2m inside the brackets. So it will become psi, the bracket part, psi star into dx, which is equal to the right hand side. And this shows that kinetic energy operator is Hermitian in nature. Now you can also see that, show that this is a very simple thing. You can see that potential energy operator is also Hermitian in nature. Like kinetic energy, there is nothing very much complicated present in the potential energy. It is a simple formula which is used. You can see that suppose there are two functions, that is psi and phi, and my operator is, that is A operator is, instead of A operator we are just taking Vx operator, that is a potential energy. Although potential energy obviously depends upon x by z, I am also just taking the Vx factor, and as soon as I put into the condition the Hermitian, both the sides will become same. So this shows that potential energy operator is also Hermitian in nature. Sometimes this kind of numerical comes because I've already splitted the numerical into two parts, one for kinetic energy, one for potential energy, and now I'm taking the totality, that is the total energy. And what is the total energy? Kinetic energy as well as the potential energy, and this will give you the Hamiltonian operator. What is my Hamiltonian operator? Hamiltonian operator is the sum of kinetic energy as well as the potential energy. So you can do this numerical into two parts. First, you can show that Hamiltonian operator is the sum of kinetic energy operator and potential energy operator. In the first part, show that kinetic energy operator is Hermitian in nature. In the second part, just tell them that potential energy operator is also Hermitian in nature. So obviously their sum is also Hermitian in nature. One more numerical, that show that if there are two operators A and B, they are Hermitian in nature, then their product AB is also Hermitian, and only if they commute with each other. So suppose the condition is already given, that is AB equals to BA, that is they commute with each other, the reversal of the multiplication is same. So what is, instead of A operator, just take AB as operator, their product as operator, because we have to show that their product is Hermitian in nature. So just instead of A operator, just take AB. So this becomes psi star AB psi, and then the condition, that is psi star, instead of AB we can take BA, and then I am taking B operator out, it will become A operator psi into d tau, because B operator is Hermitian, in fact A and B both are Hermitian. So the integral is equal to, that is A psi B psi star d tau equals to B operator psi star A operator psi d tau. So this is how you can show that, because A is already Hermitian, that AB is also Hermitian in nature. So whenever we have two operators A and B, they are Hermitian separately, then their products are also Hermitian. So in the, this is today we have finished with the topic operators. Last time I have discussed the topic operators and then I have started with the Hermitian and linear, and today I have also finished up with the Hermitian topic. So in the next lecture we'll discuss with the postulates of quantum mechanics, and I'll also do the derivation of the Schrodinger equation once again by using the postulates of quantum mechanics and steady state equation. Thank you.
With this, thank you, ma'am. Thank you so very much for giving us a productive session on Hermitian operators. And dear friends, if you want to have a particular session on a topic which has not been conducted or organized for you till now, then also you can write to us, and you can contact us through our email ID. Our ID is info.cec@nic.in. Dear friends, you're requested to call within our live sessions also if you have any queries, and you can contact us through our toll-free number, that is 1-800-110-430. But right now it's time to take your leave. We would be meeting again soon. Till then, take care. Goodbye. Thank you, ma'am. Thank you so very much.